Hello, we're Team 8, and we're happy to walk you through our Project 2, Strategize Bridge Maintenance Effectively. Here's the agenda for our presentation today. And here's a synopsis of the major findings of our analysis, including the best classification model, most important features in determined bridges condition, and a bridge maintenance prioritization framework with case studies. So, why are we interested in this bridge condition and maintenance topic? Well, last January, Fir Hollow Bridge collapsed on the day that President Biden visited Pittsburgh, the city of bridges. Although no one died, we still wonder, what are the factors associated with the risk level or condition of a bridge? The answer can help prevent potential bridge collapse in the future, thus preparing for better maintenance for the bridge and providing people with a safer living environment. In this project, we'll analyze bridge data in Allegheny County to achieve two goals. First, predict the condition of bridges based on the bridge attributes and factors that affect bridge conditions like traffic and number of historical crashes. With this prediction, the government can prioritize bridge inspection and maintenance for bridges with poor conditions ahead. Regarding the bridges that are still in excellent condition, the insight will encourage better preservation to maintain the sustainability of the bridges. And second, we would recommend some bridges to focus on regarding maintenance effort after combining the bridge conditions and other considerations such as location, data utilization, and maintenance cost. With this list, the government can strategically allocate the bridge maintenance budget. So our project uses the combination of three datasets. Our main dataset is the bridge condition dataset, which contains the latest condition and attribute information about Allegheny County's bridges. We also used a crash dataset, which provides cumulative crash data for Allegheny County from 2004 to 2020. Our main interest in this dataset is the hit bridge column to tell whether the crash hit the bridge, which can be a feature that affects bridge conditions. Lastly, we included a more comprehensive bridge dataset, which include more information about bridges in Allegheny County, like inspection, reconstruction information, and improvement costs. We would merge all three datasets for our analysis.
We implemented the analysis with these 5 steps. Before jumping to the code and machine learning, we did background studies to understand the problem domain better. We studied the type of the bridges, different components of the bridges, the material of the bridges, and the bridge maintenance process in Pennsylvania. Our analysis in particular will provide added value to the select bridge activities and maintenance work order. We manually did the feature selection. We didn't use any machine learning method to do that because we will use the other two datasets to specific goals. As you can see, we selected 15 out of 25 columns from the main dataset, and we got rid of the other irrelevant columns. For the crash dataset, since our goal is to get the number of the crashes that happen on the specific bridge, we only use 3 columns out of the 190 columns. Lastly, for the other bridge dataset, our goal is to get the latitude and longitude to join the first and the second dataset. We found some additional features that might affect the bridge condition. Therefore, we use 10 out of 173 columns. After selecting the features, we pre-process the data by merging them, fixing some of the data with these 5 steps, and create dummies for categorical variables. We also did some EDA to see the distribution of the data. As you can see, all of the numerical columns is right skewed, while the categorical variables is shaped like normal distribution. Knowing this fact, we decided to use standard scalar to standardize our data. We also see that the data is imbalanced in terms of target variables. Therefore, when building the model, we did random sampling too. After having the data ready, we split them into train and test dataset. Then we built a pipeline to do sampling, imputation, and the standardization with selected method accordingly. Using the data resulted from the pipeline, we trained the dataset with 5 models and compared their performance. Lastly, after getting the prediction result using the selected model, we explored some bridges in poor condition. We dig deeper in terms of their location, size, traffic, maintenance cost, and availability for the alternative routes. and we produce a framework that can be used to prioritize the bridge maintenance.
So as mentioned before, we trained 5 classification models and selected random forest as the best model given the highest accuracy of 0.778, while over rest AUC of 0.919, and AUC for each class all over 0.85. Since our goal is to predict the condition category of a given bridge, and poor bridges impose more threat and danger to the public, which is indicative of potential collapse, false negative is more costly than false positive, and we will focus more on recall-related positive rate and also want to increase true positive and lower false negative. In the context of bridge condition, while keeping a high accuracy, we want to have as high recall as possible, which is our highest priority. However, given the limited government budgets, we may also want to spend the money wisely. That is to say, on top of high accuracy and high recall, we can also try to increase precision if possible, to prevent spending extra energy and money on bridges which are in a good shape. According to the best model, the following top 6 most important features are associated with bridge condition classification. First, substructure condition. Second, superstructure condition. Third, reconstruction age. Fourth, age. Fifth, deck condition. And lastly, rehab or replace. These results make sense. For example, condition of substructure and superstructure of a bridge directly determines its usability, and reconstruction age and age, they indicate how long the bridge has been put into use. Older bridges will be more worn and thus subjected to higher risks. Thus, the government may want to focus more on these areas when trying to assess the condition of a given bridge. Although government can predict the category condition of a bridge given bridge features data using our model, deciding which bridge to prioritize for maintenance remains a problem. For example, among all the bridges that are classified as poor, how will the government choose the ones to prioritize the maintenance on? To answer this, we applied the framework we mentioned earlier to assess 5 bridges that are predicted as poor. The first bridge is Birmingham Bridge. It is a big bridge over Monongahela River with traffic and estimation costs provided. Since Birmingham Bridge is near many other bridges, there are alternative routes for this bridge. The second bridge is a small bridge over Plum Creek. You can see the traffic, estimation cost, and the alternative routes available as provided in the screen.
The third bridge is a small bridge over Beckett's Run. This bridge is slower in terms of daily traffic compared to the other previous bridges, but the bridge is in the Highway Pennsylvania 136. There is no immediate alternative road for this bridge. People need to go to other super far away way to get to their destination without this bridge. The fourth bridge is near the third bridge with similar condition but lower in maintenance cost. And the last bridge is a small bridge over the Little Deer Creek. This bridge is lower in terms of daily traffic compared to all previous bridges and has alternative route into it. Considering all of these 4 factors in these 5 selected bridges, this is our recommendation in terms of maintenance prioritization with 2 bridges without any alternative roads as the first, followed by the bridge with the bigger size, and followed by the costly bridges. We hope this analysis is useful for strategically prioritizing bridge maintenance in Allegheny County. Thank you so much for listening to our presentation.
Thank you.
Thank you.